Hello and thanks for tuning in once again to this channel. Today we are going to discuss about complex analysis and our topic is harmonic functions. So by definition, a function of two variables x and y is said to be harmonic and that is if it satisfies this relation equals 0. And so if you're given a harmonic function u of x, y, then it's possible to get a function v of xy such that u plus v iv of xy is analytic. So this function v of xy is called harmonic conjugate. To u of xy. So as an illustration of these concepts, let us show that this function is harmonic and also find its harmonic conjugate and express f of z so represented by u as the real part and v as the imaginary part in terms of z alone. So for the solution of the first part, so the first partial of u with respect to x is obtained by just differentiating this function with respect to x. So we'll apply product rule since this is a product of two functions and both parts of the function have got the variable x. So if I take this to be my first function, if I differentiate it, I'll get negative e to the negative x. Then I multiply by this entire function, that is x, the sine of y, minus y, the cosine of y. Then now in the next part I differentiate this second part in terms of, differentiate with respect to x. So I'll get the sine of y and I leave this constant e to the minus x. And so if you simplify this, you should be able to get e to the negative x into y, the cosine of y, minus x, the sine of y, plus the sine of y. So next we also differentiate it again with respect to x. So when you do this a second time, again by product rule, the derivative of the first part is negative e to the x. Then we'll have y, the cosine of y, minus x, the sine of y, plus the sine of y. And then the derivative of the second part of the function is negative the sine of y, and then we multiply by the first part of the function, which is e to the negative x. And so if we again write this nicely, we'll get e to the negative x into x, the sine of y, minus y, the cosine of y, minus twice the sine of y. And so next we do the same with respect to y. So the first partial derivative with respect to y is obtained as follows. So again, this is a product of two functions and only the second part has y as a variable. So this acts as a constant, and so we'll only differentiate the second part of the function. So we'll have e to the negative x, and so the derivative of x, the sine of y, is x, the cosine of y, and then the derivative of y, the cosine of y, is, so again this is a product of two functions. We differentiate the first one and get the cosine of y, multiply by the cosine of y. Then we differentiate the second part of the function and leaving the first part constant, so this will be negative y the sine of y, because the derivative of cosine is negative the sine. And so if we write this out nicely, we'll have the exponential of negative x into x the cosine of y minus y the sine of y, plus y the sine of y minus the cosine of y. So again, you differentiate this function partially with respect to y, and so this we get the exponential of negative x. So for the first term, we'll get negative x the sine of y. For the second part, we'll get the sine of y plus y the cosine of y. Then the third part will get negative the sine of y. So if we write this out nicely, we get the exponential of negative x. We'll have negative x the sine of y plus y the cosine of y plus twice the sine of y. And so if we take the second partial of u with respect to x, add to the second partial of u with respect to y, this is the second partial of u with respect to y, so the second partial of u with respect to x is the following. So what we have is exponential of minus x the sine of y minus y the cosine of y minus twice the sine of y. So if you compare these two, you notice that what you are going to get, if you take the sum of the two, you are going to get 0. So to answer the second part of the equation, and also the partial of u with respect to y is equal to negative the partial of v with respect to x. And so we are going to say that the partial of v with respect to x is equal to the partial of v with respect to y, so that in order to get v of xy, we need to integrate this partial, integrate the function here with respect to y. So we say that v of xy is equal to the integral of the partial of x with respect to y. And so this equals to, so let me just write out what we had. And so the function we're going to integrate is this function here, that is after expanding the brackets in our first partial with respect to x of u. And so in order to integrate this, we'll have to integrate this part by the product rule for integration, that is integration by parts. So if we let u to be y and then dv to be equal to the cosine of y, then in this case du will be equal to dy, and in this case again v will be equal to the integral of cosine of y, which is the sine of y. So integrating this function, so integrating y, the cosine of y with respect to y, is the same as taking the product of y and the sine of y, then subtracting the integral of, so it's uv minus the integral of v du. So we have the integral of sine of y dy. So this is y, the sine of y, and the integral of sine is negative cosine, so this is plus the cosine of y and plus a constant of regression, but constants will always be pulled together. So this gives the exponential of minus x into y, the sine of y, plus the cosine of y minus, so this part only involves integrating the sine of y, so that's the negative of cosine, so that we add exponential of minus x, the cosine of y, and then this last part is negative minus the exponential of minus x, the cosine of y. And now that we were integrating this with respect to y, and x is also a variable here, then our constant will be some function of x. So if we write this nicely, let's see what we'll get. So this is y, the sine of y, the cosine of y, x, the cosine of y, and the cosine of y. This is a negative cosine and a cosine, so we'll have the exponential of y, the sine of y, this cosine minus this cosine will give us a 0, so that we have this plus x, the cosine of y, plus some function of x. And so next we are going to take the partial of this with respect to x, and then compare it to negative the partial of u with respect to y. So if we differentiate this partial with respect to x, this is what we get. So we'll have exponential of minus, so we apply the product rule. So first differentiate this first part, negative exponential of negative x, then multiply by y, the sine of y, plus x, the cosine of y. Then next differentiate this with respect to x, so we have the cosine of y, then multiply by exponential of minus x, and then you differentiate this finally with respect to x and get the derivative of that function with respect to x. So we want to write this out nicely, so we'll get exponential of minus x. So if we open up this, we'll have x, the cosine of y, negative y, the sine of y, plus the cosine of y, then plus f prime of x. So now recall that what we had as the partial of u with respect to y, because we want to use the fact that the partial of u with respect to y is negative the partial of v with respect to x. So the partial of u with respect to y was equal to the following. We had exponential of minus x into x, the cosine of y, plus y, the sine of y, minus the cosine of y. So this was the partial of u with respect to y. So the negative of the partial of u with respect to y will be this part here. And so that means that what we have here as f of x is just a constant. And so therefore we can say that the harmonic conjugate is a function, the exponential of minus x into, and so we are going just to take this and then replace this by a constant. So it's equal to y sine of y plus x, the cosine of y, plus some constant. And so now our function f of z will be u of xy plus iv of xy, where u is defined as the function that was given, and where v is this function that we have just found. And so I'll leave you work out the third part of the question, that is expressing this function just in terms of z and to know x's and y's. So that's all we have for today. Have a lovely time, keep safe, and God bless you.